Hello, I'm Jay Patel, and my group members are Abel Apkar, Tori Hilbert, and Jacob Urich. We did the AEP Energy Challenge, and the premise of the experiment is that wind turbines can have slight vibrations when they're operating, and these vibrations can be measured using accelerometers. We want to measure these accelerometer readings and try to predict what kind of defect is going on with the wind turbine. So as you can see here, we had a accelerometer plugged into an Arduino, and we attached it to that fan, and we would be able to measure the accelerations in various directions. When you take the output of an accelerometer, this is affected by the characteristics of the turbine. So in the real world, this might be some more drag or some more mass on a particular blade. And we modeled this by attaching pieces of tape to our blades and measure the accelerometer data. So you can see here that we attached one piece of tape, but we have many different configurations that we used to measure different data. And so when we first started taking data, we realized that the accelerometer from the Arduino wasn't that good. It was only polling at about 100 hertz, as opposed to a phone sensor, which can do about 400 hertz. And the phone's accelerometer data is way better and way clearer. So we decided to just use a phone. As you can see here, we have the phone propped up against the turbines. So it's braced against it, and it gets a very clear reading because any motion in the turbine translates into motion in the phone. And so our design was various types of configurations of tape on the blades. So as you can see here, if 000 would correspond to no tape anywhere, but then 001 would be one piece of tape on one blade, and then so on, as you can see here. We ran about 2 replicates for each configuration, and about 60 seconds of data for each sample. You take over.
So after collecting the data, we then performed a Fourier analysis on the accelerations corrected for gravity, and we examined the spectral density plots to try to identify key characteristics of what each configuration's vibrations look like. We then used a random forest classifier to predict which defect configuration was present in a new vibration pattern. So on the right, we see what a typical spectral density plot looked like for a snippet in the data, and on the left we have, or on the right, on the left we have that. On the right, we have a plot of the first 2 principal components of all the data. Yep. So this model is sensitive to the structure of the turbine, and this needs to be retrained for each turbine. And also it's sensitive to the positioning of the accelerometer and the angle that the accelerometer was at. This is a plot of the different spectral densities of different configurations. And we can see that there are noticeable differences between them, which implies that we most likely can, we expect that we should be able to successfully, we expect that we should be successful at predicting the spectral densities, or at which defect it is based on the spectral densities. We used a random forest classifier, and we got a 99% prediction accuracy on which defect was present. This was measured on a validation set that was split from the rest of the data. And we expect that real world wind turbines will be more consistent and predictable than the film ones. That's time. And the recording.
So
it is
okay,
what it is.
I need that recording sent
Yeah.
in 5